Howdy. All right. Welcome to our liquid rocket PDR for Igniter's rocketry for our liquid rocket called Liquid Courage. So, to give a brief overview of what we're going to be going over, first we're going to be talking about what the Mojave Sphinx is, what our goals are for this project, the cost breakdown, our rocket configurations, and our component breakdown, and then we'll end with a risk analysis. And also, if you guys would like, you can scan the QR code so you guys can see the slides as we're presenting them. All right, so the Mojave Sphinx rocket is one of Half Cat's most cost effective and most documented rockets. They have made everything available in their book. The ground support for the Mojave Sphinx is very similar to that of hybrids, which is what we have for our IREC rocket. We also have many other teams to reference that have built Sphinx rockets in the past, which is really nice since this is our team's first experience with liquid rockets. So it's good to have like as much of a guide as we can. Another fun thing is that Half Cat allows people to register their Sphinx builds with them and get a serial number for it, and they could see your progress and it could be featured on their website. So pretty soon we'll be SN23. All right. So as stated earlier, the Sphinx is their most documented rocket. Everything can be found their in their book, which we like to call the Bible. They make it very easy to understand with a basic rocketry background. They do get into like a little bit more detail with some of their parts in construction process, which is pretty good. So the Mojave Sphinx rocket is a 4-inch diameter rocket. It's around 9 feet tall, usually. It has nitrous oxide as the oxidizer and ethanol as its fuel, specifically E85. The thrust is around 200 to 300 pound force. This depends on the injector and the launch conditions. The OF ratio is around 2.2. The chamber pressure is approximately 250 psi. The total impulse ranges from 4,500 to 6,000 Newton seconds. The reason for this great range is that no two Sphinx rockets are built the same. It really all depends on what modifications you make to it. So its approximate dry rate is around 28 pounds. The typical altitude is around 6,500 feet. And according to Half Cat, it costs approximately $1,500 to build. So our goals are to start building our liquid rocket this semester. Ideally, we want to fire this semester. There'll be more on that later. Also, we want to iterate upon the Sphinx design to, further learn and grow from this as a team. We are also wanting to enter our liquid rocket in a competition for 2027. It is undecided what that competition will be at this time. Sort of a side quest, but it would be really cool to pull up to the Liquid Symposium next year with our completed rocket. So our liquid engine name is Liquid Courage. It's the feeling you get when reading the Bible. Also, if you, not everyone knows this, but yeah, we have like 3 main rocketry teams at our school. We got us, SRT, and Red. We got more coming, but those are the 3 main 3 for now. And yeah, we're the Triforce of Courage, and we're building a liquid rocket, so the name is fitting. We would not be so confident in our ability to build a liquid rocket if it weren't for Half Cat's guidance. Okay. So, yeah, according to Half Cat, the vehicle cost is around 1130. We still have yet to make our own BOM to figure out our exact cost, but regardless, the cost is significantly lower than really any other conventional liquid design, which is another reason why we are going this route. The cost will further be lowered by utilizing components from our IRAC rocket, Thunderbolt. There'll be more information on that soon. Are there any questions? Right, moving on. So, our liquid rocket will consist of components from both our IRAC rocket Thunderbolt as well as the actual engine part, which is called Liquid Courage. So Thunderbolt is also a 4-inch diameter rocket like the Sphinx. It is utilizing a bolted assembly to couple components. And if the IRAC rocket suffers from a failure, we'll be able to more quickly amend that. So this is what the Mojave Sphinx rocket looks like. This is the open rocket file for the Sphinx. It has a cardboard airframe and is dual deploy and dual bay. These are our two open rocket files for Thunderbolt Liquid Courage, with the top half of Thunderbolt being on the top and Liquid Courage being the bottom part, which is the Sphinx part. The sim on the top is dual deploy and dual bay, and the one on the bottom is dual deploy single bay and would be utilizing cable cutters. So the Sphinx rocket per our sim goes to an apogee of around 87 feet and goes to Mach 0.609. The dual bay Thunderbolt Liquid Courage rocket goes to an apogee of 5,201 feet with a Mach of 0.538. Our single bay Thunderbolt Liquid Courage configuration goes to an apogee of 5,811 feet with a Mach of 0.612. All right, are there any questions about this? Right. Moving on. Okay. So next we're going to be going over our propulsion system. We're going to hand this off.
What is up? This is a propulsion guy. We like fire. I'm liking that stuff. This is the rocket. It's looking cool. I think you guys can agree. I'm sure you guys know. I'm sure you guys heard. We like nitrous. We like ethanol. We think it's gonna be easy. We think it's gonna take maybe two sessions, maybe one. We're gonna try for one, but yeah, it's gonna be quick turnaround. Liking that. This is another slide talking about how easy it's gonna be. Really easy and fast. We're liking stuff like that. Easy, fast. Here's our plumbing. We got two hoses for the fuel. We got one hose for the oxidizer. Why? Oxidizer falls straight down. Fuel is going to go on around the outside. What I really liked is it's just one tank. We got fuel on top, oxidizer on the bottom. Fuel is going to be pressed out with the pressure from the oxidizer. We all know nitrous is self-pressurizing. We like that stuff. We're going to use that to our advantage. We got a quick disconnect, which I don't know a lot about, but somebody else is going to talk about that later. I was kind of interested in the plumbing. I'm going to pass this over to the Skrintle injector guy. He's a cool guy. His name's Alex. My name's Noah, by the way.
Thank you so much, Noah.
Of course, man.
Howdy, y'all. My name is Alex. I'm going to be talking about the Skrintle injector that we'll be using for our engine. So the Skrintle is a combination of the words screw and pintle, where the pintle injector is a very common injector design used in rocket engines. Unfortunately, it's not a great fit for this application because it's pretty complicated to manufacture. So what Half Cat has come up with is this alternative design they call the Skrintle, where, as you can see in this diagram, you have our oxidizer. In this case, it's liquid nitrous oxide that's being injected down onto the head of the screw. Hitting the head of the screw, it's deflected radially outward, coming into contact with the fuel, which is injected into the combustion chamber via a set of radial orifices. So the oxidizer is in the middle and the fuel is on the outside. They come together, they undergo combustion, and we make thrust. So some of the benefits of the Skrintle injector is that it's significantly less complicated to manufacture, which means we could manufacture it ourselves, or if we didn't, it would be less complicated, less costly, I should say, than alternative injector designs. The cons of this injector are mostly that we're getting not as good mixture quality as we would with a pintle injector or other common injector designs. But this offers a great opportunity for us to improve our engine in the future. So the Mojave Sphinx comes with 5 basic designs for the injector, although they do encourage experimentation, especially with the injector, along with lots of other parts of the rocket. The injectors are noted by how many oxidizer holes they have and then how many fuel holes they have. So usually they're pretty similar. Sometimes you'll have more fuel orifices than oxidizer orifices, but generally the more orifices you have, the better your combustion will be, the more complete your combustion will be, and the higher your efficiency. But you'll generally have lower thrust and a significantly higher manufacturing cost. So after looking through all of these injector options, we've chosen to go with a slightly modified version of the 8-8 injector design. This design has 8 radial oxidizer holes near the screw in the middle and 8 radial fuel holes near the edge. This design gives us the best compromise of mixture ratio, giving us high efficiency and thrust along with manufacturing costs. Having fewer holes allows us to prioritize holes with larger diameter, making manufacturing easier. So to make the design, or to make the decision of our injector, we used Half Cat Sim, which is a simulation software that Half Cat provides to people making the Half Cat design. It runs in Excel, so it's pretty accessible, but you put in the parameters of your rocket and it's able to output the resulting thrust curve, thrust, efficiency, and so on. We use this software to determine which injector design would be best for us. And what we determined was that 8-8 injector would have the highest thrust. It would get us going fast enough off the rail while not sacrificing too much efficiency and impulse. These are the results of our injector. We're looking at 251 pounds of thrust and a total impulse of a little over 3,400 Newton seconds, making this an L-class motor. You can see here, compared to the other injector designs, we have a high thrust and a fairly low cost of manufacturing while still maintaining an adequate mixture ratio. I'll now hand it off to Aiden, who can talk about our more advanced fluid simulation work.
All right. So I was in charge with the ANSYS simulations, and there are basically 3 basic assumptions that I've made with the simulation. First is that the combustion is fully mixed as it enters the nozzle. So right before it enters the nozzle to go through the throat, it is assumed to have a full reaction. So that way it can simplify my initial conditions, and that way my ANSYS simulation could run a lot smoothly. This also allows me to do more iterations so that we can figure out more about different conditions that we can test out. As for the flow and the geometry, we're treating the flow as an ideal gas, steady state, uniform flow, and also there's no heat flux in going through the nozzle. So essentially, it's just adiabatic. And then lastly, for numerical, those three bullet points you see there, essentially, it's just about making sure that you have fast computations while also maintaining some precision. And then as for here, we can see the different initial conditions. And also on the right in figure 2, you can see the graph about the different values that were taken during the ANSYS simulation. And essentially what I would do is that the simulation will run. And so the residual gets to about like 10 to the -4. So that way our results are as accurate as possible. And in figure 1, you can also see how it's set up. We essentially set up a computational domain within the nozzle. And so that way we can simplify the process even further so we can have even faster computations. And then lastly, here are the results. So basically the CFD results that we got from the ANSYS is pretty similar to the Half Cat. As you can see, there's about a 6% difference in between for the thrust and the impulse. And then as for the flow field results, we're able to get some unique numbers such as the static pressure, static temperature, and Mach. And the good thing about these values is that we can do even further analysis, such as like stress analysis or even like a thermal expansion, which is why I decided to include those. Any questions? I saw you had one.
Could you say that question one more time? Oh, yes. Okay. I can answer this. You'll see a hole. Let's see if I can use the mouse. Yeah, you'll see a hole right here on the left. That is for the igniter. Ignition on the Mojave Sphinx works by first igniting a small Estes motor. I believe it's a C motor. Is that correct? It's an A, actually. Great. So we use a standard Estes igniter to light a little Estes motor, and we take out the throat in that motor. So we just get lots of flames and sparks from the motor into the combustion chamber, and that's what gets our engine started. So that little hole there is the igniter. Okay. Yep. So sure, the mixture ratio is basically it's like how much of our fuel and how much of our oxidizer is coming together and igniting. What you want is for that to be like 100%, right? Like every atom of oxygen is reacting with every atom of the fuel, right? And different injector designs will be able to get different mixture ratios. And Half Cat Sim is something that can report basically how good a mixture ratio is based on your injector design. And generally, in general, what you're going to see is the more orifices you have, in particular, fuel orifices. The more fuel orifices you have, the better mixture ratio you're going to get. But it also depends on the total amount of fuel and oxidizer you're putting into the system and other parts of the geometry. But yeah, that's right. These are from the Half Cat Sim. In general, that is true, but this is not as true when it comes to the 8-8 injector design. That's part of why we pick this design.
Yeah, pretty much. You can also see like just like in between there's also a little tiny light blue section, which is essentially just like an insert into the like nozzle. So essentially I'm just defining a computational domain of like the inside. So whatever the volume that takes up on the inside of the nozzle, I'm essentially setting that up. And so you can also see how it extends all the way out. The reason why I do that is because if I had it like a little short off from the nozzle, it'll disrupt the simulation because it'll assume that there's just like a wall there. If like let's say it stopped right at the nozzle where it ends, it'll just bounce off that computational domain and you just get inaccurate results. So that's why I also had it extend. Yeah, I see what you mean. Like you're talking about like how the fluid would expand after it exits the nozzle. Uh, yeah, I mean, pretty much I'm kind of just assuming that whatever comes out of the nozzle, it should be in like a straight line. But I understand what you're saying. Like sometimes it can like concave in or it can like go outwards. So I haven't gotten that far. The reason why I set up the computational domain in that manner is that way my computer doesn't like kill itself. That's honestly like a lot of the assumptions I made here was mainly so then I can just see if our results are similar to the half cat sim. But I'll definitely take that into consideration. Oh, I see. Yeah, I mean, initially I was thinking of having like a variable OF ratio, since the OF ratio technically is not a constant. When it gets to that throat, like it can vary slightly, but I just assumed it would not matter too much for our purposes, basically for the PDR. Maybe in the future, if we want more accurate results, sure. I guess any more tips with the meshing? This is like one of my, it's like a newer thing for me. Like the density. I mean, it's definitely a fun process. I ran this on like a virtual machine on like Tamu because my laptop cannot handle these simulations. So I guess I mean that'll be it for the question.
All right, now we're gonna move on to our ground support section.
Well, of course, because it's a liquid engine. Oh, I should introduce myself. I'm Cooper. I am a bit of a guest lecturer, I guess. I'm the ground support lead for Thunderbolt. And the reason I'm up here is primarily because the ground support for Thunderbolt and the ground support for Half Cat style rocket would be rather similar, as we will look through. So, of course, both use liquid nitrous oxide. And then Half Cat obviously uses a liquid propellant instead of a solid propellant for Thunderbolt. This is no problem, again, as we will get to. And it is definitely, it's to our benefit then that we can actually use all this. We can save a lot of money. So just briefly looking over Thunderbolt's ground support equipment, we have got a pretty simple system. You can see the diagram in the bottom left corner. You've just got an operator, somebody that sits there at the ready to control all of the valves, all of the ins and outs, the purges, everything. They're given feedback in the form of the temperature of the thermocouple on the vent line for nitrous fill conditions. We've also got a way to measure the weight of the rocket. That's another sort of separate system that we can allow the operator to get feedback in order to know whether or not the rocket is ready to launch. This is obviously all controlled at a distance. So, of course, for IREC, we have to be standing 1,500 feet away. For Half Cat, for a Half Cat launch, we would not necessarily need to be standing 1,500 feet away, as long as we have a bunker, depending on where we launch. But still there needs to be that sort of separation. It is imperative that ground support is safe. That is basically our number one priority, is making sure that we can safely operate this very, very high pressure nitrous oxide and fill the tank and the rocket. And so that's essentially the gist of it. I guess I'll go a little bit more into detail about the diagram just to give a little bit more sort of background. So, of course, the operator can sit there and press all the buttons, but at the rocket, we've got a wagon. We call it the Venga bus internally. It is a little child's wagon, essentially, that we have put all of the purge and fill valves on, as well as all of the smarts to connect between Houston, which is the operator box, and Venga bus. It's got just about everything else. It's got the batteries. It's got all the voltage regulators. It's got the pressure, the sort of analog pressure gauge. Should have just about everything that you would need for nitrous operation. And the idea is that you can just roll it out to your rocket on the pad, quick connect everything, make sure everything's good to go, and then, Bob's your uncle. Now, the Mojave Sphinx is a little different. Our system is really complicated, admittedly, and partially that's because we have a little bit more for Thunderbolt. We have a little bit more restriction. We've got to comply with everything that the RSO wants, everything that the hybrids manager Paul wants at IREC. So we have to contend with a lot more. Whereas the Sphinx GSE was a little simpler, right? They can get away with a couple of things that we necessarily couldn't get away with. And one of the biggest differences is that Sphinx decided to go with servo actuated ball valves. These are literal hand valves that you buy from the hardware store, and they have retrofitted servos onto them, 40 kilogram servos. And so, of course, that brings into consideration a lot of different things like how do you control the servos? Servos aren't necessarily like DC motors. They're not like solenoids. They have to have specific design considerations and control considerations that you have to take care of. Thankfully, for Mojave Sphinx, they actually use off-the-shelf radio control equipment for like RC planes. That's one of the sort of benefits that they're using is that they can pick all these parts off the shelf that are really cheap and use that to control not only fill, purge, and ignition. And I believe there's some other possible configurations that they talk about in the book. But just as a sort of overview, they have all the same stuff: the battery, the receiver, the way to control ignition, purge, and fill. They're just doing it a little bit differently than us. So at the end of the day, we can, our systems are really almost interoperable with some minor modifications, which we will get into later. That will be the words of the day. One of the big things, though, about Half Cat as opposed to Thunderbolt is the quick disconnect system. So on Thunderbolt, we are using a contrail motor. It's an off-the-shelf motor. We have had a good experience with assembling the contrail motors and integrating their systems into ours, or I suppose developing our systems around theirs. And specifically, one thing is that their vent line for the nitrous goes out through a center line and it purges out to the atmosphere that way. And that's a little easier for us in terms of ground support because that tube that goes down the center of the engine is burned away. It's spent. However, for Sphinx, it's a little different just because of the way that, or I suppose liquid courage, it would be a little different because of the way that the plumbing works inside of Sphinx or inside of liquid courage. So the way that Sphinx did it is they use this quick disconnect system where essentially it's a flyaway hose. So as the rocket lifts off the pad, this clip, it's 3D printed, you can see that it's kind of, I believe it stays basically stationary. And both sides of this this little connector are machined to mate with each other. And then they are connected to their respective sides, the sort of ground support side and the rocket side through flexible tubing. So as the rocket lifts off the pad, it disconnects not only because the rocket is physically pulling away the disconnect, but because of the pressure of the nitrous. And so that seems to work out perfectly well for them. And so I believe that Liquid Courage is going to be doing the same thing. The fuel we're using that Liquid Courage will be using is E85. I believe, I'm not, again, an expert on that, but that is a ratio, that's a fuel mixture of gasoline and ethanol. Gasoline and ethanol. That's what I like to drink in the morning. Funny coincidence. So thankfully, we can actually hand load that. It's not under pressure. It's obviously a little dangerous. You don't want to light it up, but it's been proven to be safe to handle, as opposed to the highly pressurized nitrous oxide that will be the oxidizer. Right. So just again, we're sort of comparing, contrasting the differences between the ground supports, and you can see other than sort of the basic differences between hybrids and liquids, uh, there's not a whole lot. I mean, of course, the ignition is different with liquid courage using a Estes motor and an Estes igniter, as opposed to a sort of typical high power rocketry igniter. And so we'll talk about it a little later, but we need to make sure that we can actually spark that thing off and not just blow it up consistently with the ignition system that's already on Vengabus. We'll have the same sort of fail safes, making sure that everything's safe, same sort of communication. And at the end of the day, really, again, there's not much different other than, I guess, the big one being the servo actuated ball valves. And to that degree, of course, I suppose this is exactly what I was talking about. This is exactly everything that we can basically reuse: the wireless transmission systems, all of the logic. Of course, there needs to be minor firmware updates, but that can be readily done. Maybe in a weekend. Really, it's not that much different. This is the big thing, of course, is that what we need to add. So Liquid Courage has two servo-actuated ball valves on the rocket, which is particularly different than than Thunderbolt. Thunderbolt, we have the two solenoid valves on the ground for fill and purge, but there has to be a way to control the flow of the liquids on Liquid Courage. And so in that case, there has to be the valves on the rocket. So that would be the job of ground support, to make sure that those fully open before ignition. And definitely they need to not open tremendously, a good time before ignition, of course, or else we would lose the flight. To that end, we would have to add some sort of PWM based servo controller. This could be anywhere from, a separate controller module allowing us to remotely talk to these things over something like I2C. The details, obviously, I could go on about. I'm very interested in the electrical portion. But essentially, just a couple of GPIO pins that are already on Vengabus need to be run out towards the rocket, is how to say it simply. We need to make sure that the servos are well fed in terms of the current. The servos have a stall current that is quite high. It is higher than the current rating of the 5-volt regulator that's on Vengabus as of last time I checked, which was last night. And so I would recommend, is I guess what I am recommending, what I'm making sure that Liquid Courage is having them do is a separate 5-volt regulator for those servos. It says updated failsafe actually on here. I'll be honest, this is exactly what we plan to have for Thunderbolt. Is just, and I talk about that in, I believe, the next slide. So we'll get to that. The ignition, as I said earlier, we need to verify that these little Estes igniters are not just going to short out immediately and not actually set off. Or we would like them to go off, obviously, but we want to make sure that they don't immediately short out under 12 volts. The sort of Estes launch controller doesn't necessarily use 12 volts, as I recall. There's just a couple D batteries in there. So I just want to make sure that we're actually able to spark off the engine reliably. And then the last thing, of course, is that going to the quick disconnect for Liquid Courage will be a little different than the disconnect system on Thunderbolt. It'll be a little different, I say specifically, because it's actually not tremendously different due to a funny little coincidence. Both Thunderbolt and Liquid Courage use 1/4-inch press-to-connect valves to connect from Vengabus to the rocket or quick disconnect. And so actually they are more or less interoperable. So not a whole lot of development needs to go on there, just a little bit to make sure, sort of checking to make sure that, you're not crazy, that sort of thing. And these are the two things I've been name dropping. I guess I should have put these a little sooner in the presentation. Vengabus is the cart, as I was talking about. That's a very early model of Vengabus, 3D model. I know it's a little too lifelike. You might think it's real, a picture, but no, I assure you that it's a hardware simulation. In any case, so that is what we're going to be using at the rocket, and then the box, as is lovingly denoted by the large text. That is what we are calling Houston. That is where the operator sits there and presses the buttons to make sure that the nitrous goes into the rocket and that the igniter is set off, as well as the two big safety keys that are in the center. So moving forward, this should be pretty straightforward. I mean, all we have to do again is add in the ability to control those servos out at Vengabus, make sure that we're not going to overload the voltage regulator on Vengabus, and make sure that, you know, that quarter-inch press to connect won't fail, or just make sure that, you know, possibly the tubing is the exact same. Really, the integration should happen rather quickly, is what I'm getting at. This is the failsafe. This is actually common between between Thunderbolt and Liquid Courage, as I mentioned earlier. Essentially, all this is saying is that upon communication loss between Houston and Vengabus, after a predetermined amount of time, again, we're still working with the range safety officer and Paul on that, the hybrids lead. After a certain amount of time, we will automatically vent the rocket to make sure that it is safe to approach. Similarly, if we have a power loss to either side, which invariably causes a communication loss, but that's neither here nor there, then we will vent the rocket. And if there is a mission abort, then we will purge the rocket. And that is all for me. I will hand it off to talk about the test stand.
Hi there, my name is Luca. I'm here to talk about the test stand. So we've recently just revised our plan for the testing campaign. Originally, we were going to construct our own homemade test stand out of 15 series aluminum extrusion. But we've decided that in order to save money and time, we are likely going to reuse existing 1515 launch rails at the Hearn and Southside launch sites. So basically, reusing these rails is going to make it a lot faster for us and a lot cheaper, because the 15 series aluminum is not cheap and it takes a while to put together and transport. So essentially, what we need to find out how we're going to modify the existing launch rails in order to accommodate tests. And primarily, we're thinking that's going to need to come with some sort of flame deflector, an upgraded flame deflector that's made to withstand the full burn of the engine instead of just the ignition. We may have to modify the way the rocket connects to the stand in order to make it stronger. We're planning on placing an adapter on top of the rocket tank so that we can adapt on a load cell, as well as hold down straps that go to ground anchors that will allow us to hold down the vehicle while it's on the pad, so that we don't have it lift off without us wanting it to. These ground anchors and hold down straps can also be modified with sandbags if we need additional weight and additional mass on top of them, but we believe that just holding it down is enough. On top of the tank, we're going to have a load cell that's going to be under pressure from the hold down straps. So by tearing that and then igniting the engine, we'll be able to measure the thrust that's output pretty easily. And yeah, we're just going to come up with a way that we're going to mount the whole load cell and hold down strap configuration to the top of the vehicle. Our main components, again, we're going to use these drilled ground anchors. What's kind of cool about these is if you take the top little hook off, they adapt to a impact driver, so we can get them drilled in and set up pretty quickly, and we're not messing around for a while. So, and they should be in pretty securely to hold the vehicle in its vertical test position. Again, I said sandbags. We can purchase those, add them for additional protection if we want to put them maybe around our ground support equipment for additional protection from the flames, or around more critical components of the launch stand. We have the option to do that. It's likely we're going to be able to reuse existing load cells from Thunderbolt to save more money because load cells are not cheap. And we can reuse the existing pads at these Fern launch sites. Okay, for the testing, we're currently targeting the second week in May, May 9th, the Tripoli Hearn launch to be our first test day. This is the day when we're going to be borrowing the rails and everything, getting everything set up. We still have to contact them and talk to them about this, but we don't think it shouldn't be an issue as far as we know. Yeah, it's a pretty ambitious date, but we think we can get everything together fast enough in order to test before the semester's over. Questions? Yes.
Right. All right, so now for our risk analysis. So with any rocket, there are risks associated with that. So some things that we are considering is our environment. We are, of course, wanting to avoid dry vegetation, so to prevent fires. The loss of our Thunderbolt rocket at IREC is also another thing that can potentially happen. So, where are you, Efren? You better recover our. You better recover Thunderbolt. Efren is our recovery lead, by the way, for context. Yeah. So ground support failures, that's another potential risk. There's going to be more detail on that on the next slide. Human error and procedural mistakes is another common thing. We're going to make sure that we write a good checklist and follow that. Of course, we'll have PPE, and yeah, we won't mess up. So, as for further elaboration on ground support, we want to not do what that beautiful diagram is showing. So we want our fire to be contained, not like that. So some of the risk areas for ground support is the servo torque under high nitrous pressure, the valve timing versus ignition timing, battery voltage sag could potentially affect the servo position. Don't want that to happen. Incorrect assembly of high pressure components. We got to prevent that too. And plumbing pressure compatibility is another potential risk area. So to mitigate these risks, we are going to have our bench test valve actuation under pressure and make sure to validate our fail-safe state physically. And we are also going to be conducting full communication range testing to make sure that everything is sound. Yeah, there probably isn't any questions about this, but just to check. Okay, on. So to conclude, yeah, thank you for joining us here at our liquid engine, liquid rocket PDR. Yeah, so I believe like most of you here are from the Texas A&M rocketry teams. So for context, us, the rocket engine design team, and the sounding rocketry team are all working on their own either like liquid rocket projects. So we are all trying to be the first to fly. So the race begins. For the red people listening, we really should drag race sometime, and good luck to y'all. And yeah, thank you for your feedback and your attendance. We appreciate that. If you have any additional feedback that you think of after this presentation, there's a QR code there for that for our form. You can fill that out and put any additional questions or comments there, or you can also just reach out to us. That works too. The link to the PDR recording will be added to this slide later tonight. So if you guys want to revisit this, you will have access to that recording. Okay. Yeah, so thank you everyone for coming out. This concludes our PDR.
Quick question for y'all, or also some comments and questions for y'all. First of all, for the ignition system, we have used Estes motors as well for our ignition system. However, the igniters that come in the package for the motors are very fragile and can break. And knowing the Half Cat igniter architecture, it will become broken during transport. So a recommendation to y'all is to swap to the Firewire initiators is what we use, and they're a lot more durable. So you don't have to worry about them breaking apart during transit.
Well, we actually are using those. Same thing for Thunderbolt, so we could just take some of those and use that.
And then secondarily, is there a reason how come y'all don't have a P and ID diagram for your entire fluid system, or even like a minor draft of it
Let's see. Which part are you talking about?
for the fluid system?
Which?
Like showing the location of the check valves.
Oh, okay. You're asking like why we don't have one right now.
Yes.
Yes. We still have to make one. So that's in progress.
Okay. And then lastly, on recommendation for some of the people in our structures for our own test stands, they are a little bit concerned with using existing launch infrastructure for the Tripoli launch sites. How much factor of safety are y'all planning on ensuring for these test stands to make sure that they don't structurally fail or they don't deform under the heat of the rocket engine during a static fire?
Primarily, we were planning on upgrading the flame deflector. That was our main thing. We figured the 1515 aluminum is pretty large and probably strong enough. We think that definitely the flame deflector is going to need to be upgraded. The smaller ones that are on the current launch stands are not nearly large enough. And we've actually seen with other half cats that they can easily destroy the flame deflector. So a current plan was to make something out of steel, probably to just keep all the flames and all that away from the legs to not cause any melting or structural deformation. But online, looking at other half cat stands that have survived it, the 1515 seems like it's more than enough.
I would encourage y'all to possibly look into either like having an ablative layer on y'all's flame deflector as an additional precaution, if y'all choose to go the aluminum route, or even if y'all go steel, also having that additional ablative layer will provide additional safety layer whenever you are going to be hot firing.
Yes, we are. We actually spoke about that earlier today. It just didn't make it onto the slides. Unfortunately, that was an oversight on my part, but we did speak about an ablative layer on top of the flame deflector.
But other than that, overall, really good job, PDR guys.
What ablative would you recommend for the flame deflector?
Currently, I believe there is one called Chamber Safe. It's a one that has been used a lot by a lot of other liquid rocketry teams for interior combustion chamber ablative material. So I would encourage y'all to see if there's something similar to that that is available for y'all to use and to mix yourselves as an additional like foundation layer for y'all to progress whenever y'all start trying to compete with higher and higher power liquid rocket engines. Having a good ablative recipe will allow you to not have to worry so much about whether or not the structural load, about having to go into more advanced engine designs, at least for the time being.
Thank you.
Are there any other questions? All right, well, thank you. Thank you for your feedback. And yeah, if you have any other comments after this, feel free to reach out. Okay, now that concludes our PDR, the real conclusion.